For thousands of years, we have looked at the night sky and believed that the illuminated stuff was all that made up our universe. Scientists now realize it's not what shines in the light, but what hides in the dark that holds the true secrets of our sky. There is a mysterious dark matter that binds stars and galaxies together, and strange particles like WIMPs, axions, and machos might be to blame. And there is a dark, repulsive energy that is creating space in the universe, but driving the galaxies further and further apart to a dismal fate. Combined, dark matter and dark energy make up 96% of the universe. And uncovering their secrets is like making the one-in-a-million shot. If uncovered, the ultimate fate of the universe might be revealed. Will it crash and burn in a horrific collision of gravitational forces? Or will dark energy tear the universe apart?
The betting is the universe will die in ice.
Understanding these two quantities, dark matter and dark energy, is really fundamental to understanding the universe.
This is a trip to the dark side of the universe. This is the hunt for dark matter and dark energy. Dark matter is unlike anything we have ever encountered on Earth. Billions of these strange particles pass through everything they encounter each second. They are so massive in weight, they have the power to influence the galaxies, how they form, and how fast they spin. Dark matter's invisible presence is everywhere, or so it seems. Science has not directly proven dark matter particles exist. There are many suspects, but no answers. And observing something you can't see isn't easy.
It doesn't emit light and it doesn't absorb light. It doesn't interact with light at all.
Not only does it not shine, you can't easily see it in obscuration.
But the evidence is there. Science knows it.
Every textbook on the planet Earth says that the universe is made out of atoms and some subatomic particles. Well, all those textbooks are wrong.
And they are going underground to prove it.
When they hear about this invisible matter called dark matter, they say, bah, humbug, show me proof that dark matter exists.
Sudan, Minnesota. 200 miles from any major city lights. A perfect place for hunting dark matter, but not for obvious reasons.
So you'd think we'd want to look up in the sky for dark matter. That's where dark matter's coming from, after all. But instead, we're going to don our helmets and we're going to walk down into this mine.
2,431 feet underground is the Sudan National Laboratory, an abandoned iron mine reconfigured into a research facility. This is just one lab of many around the world going underground to shield experiments from cosmic rays. Each are racing to detect dark matter, an invisible particle that has only been indirectly observed, but never captured.
We've been at this for now a decade, and we have yet to see a dark matter particle.
The hunt for dark matter started almost a century ago. Astronomers finally had the tools to see deep into the night sky, and the questions began.
So it wasn't until the 1920s that the technology developed well enough so that we could take little fuzzy patches that people had noticed in their telescopes and resolve them and figure out what they are.
Then Edwin Hubble shocked the world and declared the universe was bigger than just the Milky Way.
People realized that some of these little fuzzy patches are separate galaxies, just like our Milky Way galaxy.
As astronomers discovered new galaxies, Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
When he measured what the motions were in the Coma cluster of galaxies, he got an estimate for how much mass there was in that cluster. Then he compared it to how much mass you could actually see by looking at the galaxies.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see. By his calculations, there should have been 160 times more illuminated mass to account for the random speeds of galaxies in the cluster. Something else was affecting their motions. But what was it?
He analyzed their motions and concluded that the cluster could not be stable unless there was a large amount of dark matter present. In 1933, he was one of the first people to really grasp the significance of the presence of dark matter. He called it missing matter.
Dark matter, an invisible mass that was gravitationally attractive and was able to affect the speeds of entire galaxies in a cluster. Revolutionary thinking? Yes. But the discovery was largely ignored.
I think that people took Zwicky seriously, but they didn't jump to any conclusions. This was a time when the universe was just beginning to be explored. It was the 1920s when we first realized there were galaxies outside our own. What we didn't know back then was whether it was simply galaxies or stars or gas or dust that we couldn't see, or whether it was something truly different.
Zwicky's observations were based on measuring the mass in the stars and galaxies. But how do you weigh stuff in space?
You can't go and put the sun on a scale. That's a little bit hard. But what you can do is you can measure how fast the planets are moving around the sun. And the more stuff there is in the sun, the faster those planets have to move to stay in their orbits.
Newton and Einstein both said the more mass or stuff you have in an object, the more gravitational pull it will have. And the further an object is from the center, the slower it should travel in orbit, because the gravitational pull is weaker.
According to Einstein's general theory of relativity, or even according to Newtonian gravity, all of the galaxies are pulling on each other.
It's like the sun's influence on our solar system. The mass of the sun pulls Mercury faster than Pluto because Mercury is positioned closer to the sun.
Likewise, for a galaxy, you would expect that as you got further and further away, things are moving more and more slowly to stay in their orbits.
But Zwicky didn't observe that. Neither did a young scientist named Vera Rubin 50 years later. She was observing the rotational curves of galaxies similar to the Milky Way. Like Zwicky, her observations also seemed strange.
What Vera Rubin actually measured was that as you got further and further away, the velocity of the orbiting gas and dust remained constant.
What Rubin observed was as if a city were a galaxy and every car on the road was a planet or star. And despite the amount of traffic, every car traveled around the city at the same speed. This same consistent rotational speed, despite the amount of stuff or traffic, was exactly what Rubin observed.